This video is on section 4.2 notes, logarithmic functions and their applications. So first, you can see that a logarithmic function is defined based on an exponential function. So they're saying that log with a base of x is only true if the base raised to y equals x. And they use the letter a here, but I'm not going to use the letter a because we typically think of that as a transformation, as a kind of a coefficient in front. So I'm just going to think of that as b as a base. So if we think of these problems in terms of this definition right here so that we can kind of evaluate these logs, then we have to think of this as the base to some exponent ends up equaling whatever you're taking the log of. So 3 raised to some exponent equals what I'm taking the log of, which is 9. So 3 squared is 9, and that's the solution, or that's the evaluation. So here the base 2 to some exponent equals 1/4. And I have to think about, well, how do I get a base of 2 and become fractions? And that happens when I have negative exponents. So this would be 2 to the second, but to make it a 1/4 instead of a 4, it has to be to the negative 2. I almost said negative second, and that would have been weird. Okay. And then over here we have 1/2 raised to some exponent is going to give us a result of 8. And I have to think about, maybe if I think of it as 2 raised to some exponent would give me 8. That would just be 3. So to take something that's written as a fraction and get a whole number from that, it just means that I would have to raise it to a negative exponent. So this would be -3. Sorry, that was my phone ringing. And I'm going to show you guys how to evaluate these in your calculators in case these answers don't feel as clear to you. And when we first start working with logarithms, they're going to feel uncomfortable. And the longer we work with them, the more clear these things are going to get. So these might have felt difficult right now, but by the time we do section 4.2 and 4.3 and 4.4, you should be able to look back at these and say, like, no, I could figure those out pretty easily. All right, so if we wanted to type this into a calculator, I would hit the math button and I would go over to, what was it, number? I should have looked up this ahead of time. There it is, log base. So you're going to hit the math button and go up in your calculator, and it says log base, and that's how you type it in. Log base 3 of 9 is 2. For the next one, hit the math button, hit up, log base 2 of 1/4 is -2. Hit the math button, up, log base 1/2 of 8 is -3. And then if you're working with one of those color additions, I believe instead of hitting up, you hit up 3 times. So you'd hit the math button and go 1, 2, 3, and then it would, because you have a different menu than we have on these calculators. Okay, next we have 2 specific types of logs. So one is log of x, the other is ln x. And both of these just mean specific logs, log base 10 of x, and this one is log base e of x. So in this one, the base is 10. Powers of 10 tend to be pretty common, and so that's why they call it the common logarithm. This one is using Euler's number, 2.7. They call that the natural logarithm, and I'm not sure why. ln, maybe it has, I don't know, something to do with Latin, who knows. So these are 2 things to keep in mind. So when I'm working with something like this and I'm trying to evaluate them, I have to think about, okay, what this base to what exponent would end up giving me this result. So if it just says log, that means that the base is 10. So 10 to some exponent gave me 1,000. And if you know your powers of 10, then you know you can just count the zeros, 1, 2, 3. So this would be 3. ln is really log base e, So e to some exponent gave me a result of 1. Well, the exponent that would do that is 0. Anything to the 0 power is 1. Here, a base of e to some exponent gives me a result of -6. That's a trick question. Whenever you deal with exponents, you can never get 0 as an answer or a negative number as an answer. So this is undefined. And we can do these in our calculator as well. Since these are common types of logarithms to do, they actually have their own button. So we have the log button right here and the ln button right here, or natural log button. So log of 1,000, that first problem, is 3. Ln of 1 is 0, and ln of -6 is undefined because you can't do it. Okay, so next we're going to look at how to graph logarithmic functions, and logs are actually just the inverse of, or the opposite operation of, exponential functions. So if you have a base to an exponent that's a variable, to undo that, you would do a log with the same base, and we'll talk about that more later. So the important thing to remember here is that if they are inverses of each other, then that means that to graph them, we just have to trade the x and the y coordinates. So if we have y equals 2 to the x is one function, then its inverse function would be y equals log base 2 of x. And so these points would be 1/2, -1, 1, 0, 2, 1, and 4, 2. And then instead of having a horizontal asymptote at y equals 0, we would have a vertical asymptote at x equals 0. So I'm going to go ahead and draw in this vertical asymptote. And we've got 1/2, -1, 1, 0, 2, 1, and 4, 2. And so a log graph looks like that. All right, so we talked about it briefly in the previous video, but when you're graphing an exponential function, you only really need these 2 points and the horizontal asymptote. So if you have y equals b to the x, where b is the base of the exponent, then the 2 points that you need are 0, 1, 1b. Whatever the base is what that number is going to be. So if it's 2 to the x, you're going to have 2. If it's 5 to the x, you're going to have 5. If it's 1/2 to the x, you're going to have 1/2. And then you're always going to have that horizontal asymptote y equals 0, at least for the parent function until you've done transformations. Over here, if we have log base b of x, then you're just going to take the inverse of each of those. So you're going to trade the x and the y. You're going to have the point 1, 0, you're going to have the point b, 1, and you're going to have a vertical asymptote at x equals 0. So that's what we're going to use today to be able to graph our logarithmic functions. So if we turn to the next page, we have ln x, which is just y equals log base e of x. So we don't have to be intimidated. We know that it works the same as logs, and we know from previous notes that e is approximately 2.718 or 2.7. It's just Euler's number. So we have the point 1, 0, the base, 1. So I'm just going to say 2.7, 1, and then the vertical asymptote is 0. So I'll graph that vertical asymptote. We have the point 1, 0, the point 2.71, and the graph is going to look like this. Over here, the base is 1/3, so I'm going to have 1, 0, 1/3, 1, and a vertical asymptote of 0. So 1, 0, 1/3, 1, And so it's going to look like that instead. Okay, so here we have our logarithmic function. They used their base as the letter A, but I would use my base as B. So they're saying the function is increasing if the base is greater than 1, like in this graph, or it's decreasing if your base is between 0 and 1, like in this graph. The x-intercept is always 1, 0. The graph always has the y-axis as a vertical asymptote. The domain of the graph is from 0 to infinity. The range of the graph is all of the numbers, all real numbers. The function is 1 to 1. That means it has an inverse. You can find the inverse. And then log and exponential functions are inverse functions. All right, so here are the parent functions. Here are the transformed functions. The transformations work exactly the same as what we've studied in the past. So the number in the front is a vertical stretch or a vertical compression or shrink. If it's negative, you would reflect the graph over the x-axis. The inside of the function is where the x is, and so that would shift the graph to the left if it's got a plus, to the minus if it's got a to the right if it's got a minus. And then if there's a number on the end, you're going to shift the graph up or down. So we're going to look at two different graphs that have transformations, and we're going to find the domain and range of each of them. So here we have log base 2. So I know that for my parent function, that's going to give me the point 1, 0, and then base 1 and a vertical asymptote of 0. That's just the information that I'm starting with. And then I can go ahead and do these transformations. So my transformations are that the graph is reflected over x, and the graph has shifted to the right one. So I'm going to take these points and reflect them over x. So my x coordinates are going to stay the same. My y coordinates are going to multiply by a -1. And if something has been reflected over x, I have a vertical asymptote and my graph went from here to here, that's not going to change where my vertical asymptote is. So my vertical asymptote is still here at 0. And then for the graph to shift to the right one, I'm going to take each of the points from here and add 1 to them. So right 1, right 1. I don't have to shift the graph up or down at all, so I'm going to keep these points the same. And then for the vertical asymptote, if I have it at 0 and I shift it to the right one, it's actually going to move. So I'm going to shift the vertical asymptote to the right one. So here is the vertical asymptote for this function. And then we have 2, 0, and 3, -1. And so the function should look like this. All right, for the next one, we can think of this as y equals 1/2 log base e of x plus 3 plus 1. And so my starting points are 1, 0, and then the base, 2.7, 1, vertical asymptote at 0. So I have 3 transformations. This graph has been vertically compressed or vertically shrunk by 1/2. It has shifted to the left 3 and up 1. So to vertically compress it or vertically shrink the graph, I'm going to take the y coordinates and multiply them by 1/2. The vertical asymptote is going to stay in the same spot. Then I have to shift the graph to the left 3. So 1 to the left 3 is -2. 2.7 to the left 3 is -0.3. And then shift the graph up 1. So 1, 1.5. And the vertical asymptote, if I have the graph, the vertical asymptote right here, shifting it to the left 3 would actually move it. Shifting it up 1 wouldn't actually move it anywhere. So vertical asymptote x equals -3. So we have -2, 1, and negative 0.3, 1.5, like there-ish. So the graph would look like this. All right. Next, we're going to convert each of the following into their inverse form, or the opposite form. So to do that, I just want to learn a little bit about the inverse operation so I can think about how to efficiently write this. So I know that the opposite of log with a base of 2 is an exponential expression that also has a base of 2. So to undo log base 2, I'm going to create an exponential expression with a base of 2. And I'm going to do that to both sides. Exponential expression with a base of 2. So this is 2 to this exponent. This is 2 to that exponent. Now, since these are inverses of each other, a base of 2 and a log base 2, they cancel each other out. And I end up with 32. And then on the right side, nothing cancels out. I just have 2 to the 5th. And that is a true statement. 32 equals 2 to the 5th. Okay, so I'll try the same thing over here. I want to get this into the exponential form. To undo the log, I'm going to use the exponential form with the same base. So that's a base of 5. 5 to all of this as an exponent. 5 to 2 as an exponent. So these cancel each other out. And I have 5 to the second power equals 25. Again, that's a true statement. Here I want to get rid of log base 11. So I'm going to do that by using the inverse operation, which is writing 11 as a base and all of this as an exponent. So 11 as a base, this as an exponent. So these cancel, and I have 11 to the -2 equals 1 over 121. And that is true. Okay, so here we want to take the exponential expressions and write them in their log form, and we're going to do that by undoing the base of the exponent. And to undo the base of the exponent, you have to introduce a log with the same base. So on the left side, I'm going to put a log with a base of 3, and on the right side, I'm going to put a log with a base of 3. So log base 3 of 3 to the 4th power, the log base 3 and the 3 cancel out, and you end up with just 4. And then on the right side, we have log base 3 of 81. So log base 3 of 81. And I can check that to make sure it's right. Math, up, up. Log base 3 of 81 is 4. Okay? Over here, the base that I want to get rid of is a 9. So I'm going to do log base 9 on the left side, log base 9 on the right side. The log base 9 on the right side and the base of 9 cancel out. And so I just have a 2 on the right side. On the left side, that log doesn't cancel out with anything. And so I have log base 9 of 81. So I just want to make sure that log base 9 of 81 is 2. Log base 9 of 81 is 2. Okay, for this last one, the base is 1/3. So I'm going to do a log base 1/3 on the left side, a log base 1/3 on the right side, and the log base 1/3 and the base of 1/3 cancel out. And I get -1 equals log base 1/3 of 3. And I can just make sure I got that right. Log base of 1/3 of 3 is -1. Okay, so now we're going to take that idea of inverses, knowing that logs and exponential functions are inverses of each other, and we're going to go ahead and use that inverse operation to actually find the inverse of each function. So if you guys recall, the first step to finding the inverse of a function is to trade the x and the y. And then you just have to undo each operation until you have solved for y. So when we get to problems like this, it can be kind of confusing to figure out what operation needs to be undone first. And so the best way to remember is to just think about order of operations, PEMDAS, or please excuse my dear Aunt Sally, to do those operations, but to do them in backwards order. So the first one is add, subtract. Second is multiply, divide. Third is exponents, and then fourth is to get inside of any grouping symbols, whether they be parentheses or something else, and then you start the process again once you get inside the grouping symbols. So if we're solving for y, first thing we would want to look at is there anything we could add or subtract to the other side? And there's nothing, because this exponent kind of has stuff trapped and the exponent's not the first step. So next we're going to say, is there anything I could multiply or divide to get things to the other side? And yes, I can. I can multiply by 2 to get the 1/2 over, or I could divide by 1/2, but multiplying by 2 is a little bit easier. So I'm going to say 2x equals 6 to the y minus 3. Next, if I want to get into the exponent, then I have to get rid of the base. So to get rid of the base, I'm going to log base 6 each side, log base 6 and log base 6. So the log base 6 is going to cancel out with the base of 6, and I'm going to end up with y minus 3. On the left side, you can write log base 6 of 2x, and you can put the 2x in parentheses or not put it in parentheses. It doesn't matter, but you have to keep in mind that the log happened to the 2x, and anything that comes after it, the log does not influence. So I'm going to go ahead and put parentheses here just so you can see with my final answer what I mean by that. So we didn't have any grouping symbols, but we did get inside the exponent now, so I'm going to go back to the beginning and go through the steps again. So to get the y alone, I can add or subtract. I'll move the 3 to the other side. So I have log base 6 of 2x plus 3. And I'm going to write this in my inverse notation. So log base 6, and you can write 2x plus 3, you can write it like that. The log base 6 is of the 2x, the plus 3 is just hanging out on the end, or you can put the 2x in parentheses. That would be correct as well. What would be incorrect would be if you put parentheses around the whole thing, 2x plus 3. That would be incorrect, but writing it like this is fine. And writing it without the parentheses is fine as well. All right, for the next problem, I'm going to put the y right here. So first step is to trade the x and the y. And then I'm going to go through my order of operations backwards. So is there something I could add or subtract to the other side? Yes, there is. I'm going to subtract the 4. X minus 4 is log base 2. Y minus 1. Is there something I could multiply or divide to the other side? No, there's not. Here, is there anything I could do with exponents? And the answer is yes. If I put a base of 2 on each side, that's going to get rid of my log, and it's going to create this as like now we have an exponential function. So base of 2 to the log base of 2, those cancel out, and we just have y minus 1. And then on the left side, we have 2 to the x minus 4. And then at this point, I've gotten inside my grouping symbols. My grouping symbols were kind of trapped by the log and then the parentheses, so I'm inside the grouping symbols, and I can go back and start the process again. So what can I add or subtract? I can move the 1 over. And the 1 is not inside the exponent because it happened afterward, so it's just tacked onto the end. So my function is f inverse of x is 2 to the x minus 4 plus 1. Okay. For this last one, I'm going to take my x and my y and trade them. And then I'm going to walk through my steps. So first step, add or subtract a number to the other side. I can move the 5 over. Next step, multiply or divide a number over to the other side. I can divide the 3. Next step is deal with the exponents. So here I need to get rid of the base so I can get to the exponent. And to get rid of the base, I need to do log with the same base on each side. So log base e, log base e. So the log base e and the base of e will cancel. You can write this as log base e of this fraction, but most people don't. Most people would say, oh, log base e, that's ln. I have no idea if my math lab would mark you down for that or not, but technically you would be right if you wrote log base e. So ln, and you can put this in parentheses or not put this in parentheses. It technically doesn't need parentheses, but it might feel strange to write it. So ln of all of this stuff equals y minus 1. And now I've gotten inside of my exponent, kind of inside my grouping symbol, so I'm going to go back to the start and add or subtract to get the y alone. So I'll just add y to the other side. And all of that stuff happened first, and so the 1 is just going to be tacked onto the end. So I have y equals ln x minus 5 over 3 plus 1. Technically, you don't really need the parentheses, but they feel kind of helpful in this case. And then I'm making sure that I'm writing my final answer in that inverse notation. All right. On the next page of notes, we have solving exponential equations using logarithms, which means we're going to be using that inverse operation to help us solve. So if you think about what we did in the previous section, we would say, well, this has a base of 10 and that has a base of 50. So how could I rewrite it so that both of these sides of the equation had the same base? Except the problem is for this equation, you can't. It's not possible to do that. So this is another method to solve exponential equations when you can't possibly rewrite both sides of the equation as the same base. They're not both a base of 10 or both a base of 4 or both a base of 2. So here, if I want to get to the x, I just have to undo the base of 10 so that the x will be alone. And to undo the base of 10, I'm just going to have to log base 10, the left side, and log base 10, the right side. So that cancels out the base of 10. So x equals log base 10 of 50. And we know that log base 10 is that common logarithm where you don't actually have to write the base. So you can just say x equals log 50. And we can type that into our calculator, log 50. And if you forgot and you went ahead and used the math button, that's fine. You can do log base 10 of 50 and you're going to get the same answer. So 1.699. All right, for this other one, I'm going to go ahead and isolate the x. So I'll divide by 2 first. I get e to the 0.5x equals 3. Next, I want to undo the base of e. So I'm going to log base e, the left side, and log base e, the right side. And that cancels out the e. So I have 0.5x equals log base e of 3. And this is not mathematically incorrect, but most people would not write it that way. Most people would say ln. And then I'll just divide by 0.5. So x is ln 3 divided by 0.5. So that's 2.197. If I wanted to type it in the other way, because I left it as e, then I would just do log the e button automatically says e to what power, I'd have to do to the first power because that's just plain e. Log base e of 3, and then I'd have to take that answer and divide it by 0.5, but I would still get the same result. So it doesn't matter if you don't recognize those in the moment, you can still mathematically get the same answer. People would just kind of frown at you. Math people would kind of frown at you. Nobody else would care. Okay. Next example says if $8,000 is invested at 9% compounded continuously is PERT. How long will it take for the investment to grow to 20,000? How long would it take for the investment to triple? So we have two scenarios, 20,000 and triple. Okay, so for it to grow to 20,000, we know that 20,000 is our end result that we want. We started with 8,000. We had a rate of 9%. And t is what we're solving for. So to solve this problem, we're just going to divide by 8,000. .5. 2.5 equals e to the 0.09 t. To get rid of the e, I'm going to log base e both sides. If you get comfortable with this and you start to say, well, the opposite of e, or to undo e, I just need to do an ln, and you want to write it like that instead, that's totally fine. So log base e is really just ln. And then to get the t alone, I just need to divide by 0.09. So ln 2.5 divided by 0.09, 10.181. Okay. This one, the second question said, how long does it take for the investment to triple? So they didn't give us a dollar amount, they just said triple, and we just have to know what that means. So if the initial investment was 8,000, then to triple that, we need 24,000. So triple is 24,000. So 24,000 equals 8,000 e to the 0.09 t. And we can just follow these same steps that we did before. 24,000 divided by 8,000 is 3 because it tripled. And then we can get rid of the e, so we're going to log base e on each side, or ln each side. And then get the t alone by dividing by 0.09. $12.207. So the big takeaway from these notes is to make sure that if you need to, that you know that if you need to undo a log of a certain base, you just have to rewrite it as an exponential problem with that same base. And if you have an exponential problem where you have like 2 to the x or 5 to the x or something to the x, and you want to undo the base of an exponent, you just have to introduce a log with that same base into the problem. That's the big idea for today.